Today we are doing our third experiment, and this is motion along a straight line. And of course, you already learned the theoretical part of motion. I mean, in the theory part, right now you're learning equations of motions, and it is one of that kind of an experiment. And our experimental objective is to find the acceleration of an object in an inclined plane. Before that, I would like to introduce you about the lab instruments that we will be used most of the time. This is the table that, and it's in fact it is a frictionless table, and you most of the time we will use this table, or we call it the track. It's a track, and we have a cart, and this cart you can see that it is in fact it is a frictionless track, and by the combination of these two it becomes a frictionless motion, so that it will roll forever. Actually, this is the this setup we will be using for almost all our experiments. Now, here I wanted to introduce you about the two things that we are going to use mainly in our experiment. You can see that this is an interface. This is called LabCust Mini. This is from the Vernier company, and in fact, this interface is connected. This interface is connected to the computer, and there's a program called Logger Pro. Most of the day we will use that program, and you can see that this is a sensor, and this sensor is connected to the interface, and the interface is connected to the computer. And this instrument or this interface is capable of doing a lot of measurements. And in fact, we will use in different experiments. And today, different sensors. We can use maybe whatever be the sensors you prefer. If you wanted to measure a force, you can connect a force sensor. But today we are connected with this, a motion detector. And what is motion detector? Yes, this is the sensor. This sensor will send sound waves. And if I keep this in this track, you can see that if I connect this to the track, I'm connecting this to the track, okay, and this is connected to the interface, and it is connected to the computer. Now, if I move this sensor can record each and every moment of its motion. That means this will send a sound waves, and it reflects back, and each and every moment its time and displacement can be recorded using the program, and the program is capable of providing us whatever we are expecting. I mean, most of the times you learn the theory that we will do velocity time graph. I mean, if I want the velocity, if I try to move it, its velocity and time, I can easily plot there. If I wanted to see the displacement of this along, I mean, with respect to the time, I can observe it in the screen. That means this setup will provide a complete idea of its motion, the way that we want, by the help of the computer program. And today, you know that our today's experimental objective is to find the acceleration of this object in an inclined plane. So that's why I'm going to keep it in an inclined plane. I'm going to make it in an inclination of a little by keeping this two masses here, so that you know now this track is now inclined. And of course, you learned right now that if I keep this object, it will be accelerated. Yes, why it is accelerating? Of course, you learn now. It is accelerating because of the force acting in this direction. And of course, you know that the force, this is the force mg is acting downward. Its sine component mg sine theta is the force acting on this. And because of that force, there is an acceleration, and we know that the acceleration is a equal to g sine theta. That means there is an acceleration. So in this moment, if I leave this, it will be accelerated, and the acceleration of the object is g sine theta. And of course, you learned the method of measuring its angle of inclination by taking the heights. I will show you that in a way. But before that, have a look. If I drive this to up, it will be rolling up and coming down. And I have a question to you. What will be the acceleration of this object all the time while it is moving up or down? Which direction the acceleration is? Which direction the force is? Yes, your answer is correct. The force is this direction. So the acceleration is all the time in this direction. While it is rolling up or rolling down, its acceleration is always towards this direction, and it is g sine theta. and g we know that 9.8. And if you can find the angle of inclination here, you could able to find the experimental value of or theoretical value of this acceleration. That means if I leave this, definitely you will be able to calculate the acceleration of that, and by the help of this setup we can verify that acceleration is the calculated acceleration and the experimental acceleration are same or not, and that is our today's experimental plan. I will explain you in details now. Okay, so we are going to, in order to calculate the acceleration, we want the sine theta. That means the inclination of this track. If you look in this track, is it easy for us to find the angle of inclination, this small angle of inclination? It's not so easy. Even if I use a protractor, I will get very bad result. So I'm going to calculate this. I'm going to measure this angle in a different approach, a mathematical approach. Have a look how I'm going to do this. You can see that this is the, imagine this is the track, and of course this is the base, that means the tabletop. Okay, if you wanted to know the angle of inclination, that means you need to extend it, right? So this is the angle of inclination, but it's not so easy to measure, right? So I'm going to use a very simple mathematical method. You can see that. See, what is our plan? I'm going to take two heights, one from this point, and let's say this is the first height I'm going to measure, h1, and another height here I'm going to call h2. That means if I have a scale, I can measure this height. Let's say this height is, and another height from here, let's say the small one I call h1 and the bigger one I call h2. And of course, this distance between them, I can notice it from my track. Usually, imagine if my plan to keep it at 30, that means I'm taking the height of 30. This is h1. I can read it very clearly here. And I'm going to take the height here, h2. I can read it very clearly from here. And of course, this point is at 30 and this point is at 90. What's the difference between 30 and... So that means this is we call 60. So this distance, imagine it is d, and I know that it is. So look, if I have a situation like this, how could it give me the angle theta, the inclination of theta? If I have these three measurements, I will be able to do the angle of inclination calculation. How? Have a look. If I draw a parallel line, to the table, that means this is a table surface. If I draw a parallel line, yes, these two are parallel lines. So that means if I extend this, that means this angle theta and this angle theta are corresponding angle. Am I right? Now, if you know this height and this, it will give us the thing that we want, the angle of inclination. In fact, in our today's experiment, we want acceleration. We know that acceleration is g sine theta. That means we want sine theta. Oh, that we will get directly from here. What is sine theta? We know that sine theta is opposite side over hypotenuse. Yes. So here what is opposite side? Here the opposite side is this, right? Because this is the angle theta and its opposite side is this. Oh, we know that this height is h1 and this total height is h2. So this is opposite side. Definitely, yeah, the opposite side is h2 minus h1. And what is the hypotenuse, the angle opposite 90? Oh, this is the hypotenuse. So the hypotenuse is d. So that means sine theta is opposite side, that is h2 minus h1 divided by this d. Here from this setup we can easily measure h2 and h1 and d. Thus we will reach sine theta. And now we'll be able to find our acceleration theoretically. The theoretical acceleration is g sine theta. That means d h2 minus h1 by d. So we'll be able to calculate the acceleration before we do it using the setup that we have. I'm going to run it now by using this computer program, and you can able to see that we will see both of the answers are same or not. or we will verify that. Okay, so we are going to do the first trial, and of course we calculate the theoretical value of the acceleration, a equal to g sine theta, we calculated, and now we are going to verify the same reading using the computer setup that we have, the sensor and stuff. So what I'm going to do, I'm going to roll this little up by pushing this way. So what will happen? The moment I leave it from my hand, there is no force from me on that. This is only moving under the influence of gravity. And while it is rolling up, I'm going to start the logger program, and you can able to record the reading. So what I'm going to do, I'm going to start the start button. Okay, I'm going to click the collect button. So now see, yeah, you can see that the moment I click the collect button, the system is taking readings. But when I bring something in between, it automatically stops after 5 seconds. Imagine, but nothing is moved. But if I start it again, and the moment I start, and if I push this up, you can see that the motion is recorded, and it stops after 5 seconds. And there is an option for me here to auto scale, because this is the scale of the position and time. So this is the option. I'm going to click on the auto scale option, and the motion is recorded, and it is the velocity time graph, and this is the position time graph. And you can see that during this time the cart was at rest, and this time I push, and after that the cart is moving under the influence of influence of gravitational force, or it is a free fall, or it is only under the acceleration of g sine theta. So this is the area the object was moving under the g sine theta acceleration. And of course this time it stops, and we immediately, actually it's a velocity time graph, right? If you have a velocity time graph, you know that the velocity time graph will be a straight line, because the motion of the object is uniform. So it is a uniformly accelerated motion. So the slope of the graph represents slope. What is the slope of the graph? It is v by t, velocity by time. It is acceleration, right? And here we have a position time graph, and you can see that during this time the cart was at rest, then the cart is moving under the influence of mg sine theta, that force. That means it is under an acceleration, a equal to g sine theta. So that's why we have a parabolic path. And now our idea is to get the acceleration from this graph and this graph. See, I get this, you understand the idea. Now if I want to take one, imagine if I want to repeat this, just collect the button and push it again all the way up, somewhere you wish. See, the reading is not good. So what I will do, once again I will start and push it little bit. So I can take the reading as much as I want, right? So now I have a good reading, and today what's my plan? My plan to understand the slope from this velocity time graph. Actually, because it's a computer aided stuff, so I can easily fit this, because I'm going to select the straight line, I'm going to fit this to the computer program. Here I have an option to fit this into a line. You look at this, so the computer is automatically fit this into a straight line, and the slope of the graph is here very clearly seen. Actually, it's a straight line relation. We know that, the equation of a straight line. In fact, here they write v equal to mt plus b. In fact, it is v final equal to v initial plus at. This is the velocity time relation for a uniformly accelerated motion. So look at this. So what is the slope represents? The slope m represents acceleration. So that means directly I can tell the acceleration of this object is 0.4498 meter per second square. Am I right? Once again, what is this? It's a straight line equation. That means we know that it is y equal to mx plus c, right? It's a straight line, and of course, because it's a motion of an object in a uniformly accelerated motion, so the relation is v final is v initial plus at, so the slope represents acceleration. Now we know that it's a displacement time relation, and everybody know that the displacement time relation is x final equal to x initial plus v initial t plus half at square, right? And this is a relation you already learned in the theory class. X initial plus v initial t plus half at square, right? Actually, what is my plan? Have a look. I'm going to fit this into a parabolic part, because you know that's an equation of a parabola, y equal to ax square plus bx plus c. So I'm going to fit this into a parabola. Here I have an option for curve fit. You can see here, I click here the curve fit, and here there are many options to make the computer to fit this into. Actually, we know that this is the relation, the quadratic relation. So I'm going to choose the third one from here, at square plus bt plus c. And now what I'm going to do, I'm going to try fit, put OK. The moment I did it, the computer is provided all the informations what we need. X equal to, what is the equation of this parabola? It's given here, x equal to at square. Look here, at square plus bt plus c. Have a look. The coefficient of t square is half acceleration. The coefficient of t is initial velocity, and the c is the initial displacement, xi, right? Initial position. So from this, what is the value of a? The computer is given us the value of a. A is 0.2218. That means this is half. A is what? Look here. A is what? Half a. That means this is half acceleration. Half acceleration is equal to 0.2218. Therefore, acceleration is 2 times 0.2218. So it will be 0.4436 meter per second square. Am I right? So I have the value of acceleration, the experimental value of acceleration from two methods. One, I calculate we determine the acceleration from the displacement line graph, and that is 0.44. And also I did it from the velocity time graph, that's also 0.44. They are very close. Yeah, there is a small difference in the last digits. That's normal. So we already have the value of the theoretical value. Now you compare it. You will see that these two are very close. Let me show you that. Okay, now we are doing the second trial. So what I am going to do, my plan is to increase the angle of inclination. If I increase the angle of inclination, what will happen? If I increase the angle of inclination, my plan to keep another two mass here so that I can just put this a little bit higher, so that now the angle of inclination is increased, and of course the acceleration will increase, right? Why? We know the relation. What is acceleration? Acceleration is equal to g sine theta. Here g is a constant. That means the acceleration is proportional to sine theta. Yes, if I increase the angle theta, acceleration will increase, right? So what I'm going to do, okay, in our experiment, what we will do, we'll find the h1. If I'm going to keep it at 30 centimeter, this marking is 30, so I will get h1. If I keep it at 90, I will get h2. So h2 minus h1, and this d 60, I can easily calculate the theoretical value of acceleration. Now, what I am going to do, I will do the same way. I'm going to run it, then I will get. So I will get another acceleration. Now I have a set of acceleration for different heights. So what did you notice? For the first trial, the angle theta was small. Now I increase the angle theta. So you will see that the acceleration is increasing, and the acceleration is proportional to sine theta, right? So that's our experiment. That's all.